My guest today is Stephen Andrews.
I've titled this one the same title as I had before, Climate Change, Further Evidence Contrary to the Accepted Narrative. This is part 2, The Missing Links. And you'll see why I called it that, hopefully later on in the presentation. I'm going to do a quick recap from my previous presentation. My background was my training and education has been primarily in science, studying biochemistry, chemistry. I worked in the pharmaceutical industry as an analyst and the quality assurance sector. I write on my Substack. I'm currently retired. And I also write for the Daily Sceptic, the odd article. And in fact, I'm going to be submitting an article to them. If I don't know whether they'll accept it, because sometimes it slightly clashes with their approach. You had Chris Morrison, Tom had Chris Morrison on, who's the Daily Sceptic, sort of climate change editor, environmental editor. And anyway, I will submit it to them. They usually always put a link to it, but as their name suggests, they tend to provide a contrary view. My previous presentation was on October the 16th last year, and it covered the following, really: my data-driven journey from a climate change doommonger to an anthropogenic, that's carbon dioxide-driven climate change denier. I concluded that cosmic rays are a primary driver of recent climate change. This presentation I'm about to give provides additional evidence that supports a combination of two hypotheses. Both these hypotheses have been voiced on Tom's podcast, and I'll be referencing them later. What is my approach, and what data am I using? I'll be using data from a number of sites. All of these are massively pro the accepted narrative. Many of them are quite expensive sites, facilities to run. And of course, they need quite a lot of funding, and largely a lot of that funding comes from governments. And so if they don't sort of go with the accepted narrative, that they don't get funding. So the sites I've used are Berkeley Earth. I believe that's the California-based ones. They have an extensive global temperature record. NOAA, the National Oceanic and Atmospheric Administration. NASA, the National Aeronautics and Space Administration. I used data, this is from the cosmic ray data I'm going to use, is from the University of Oulu in Finland. And I've also been citing work from CERN on their cloud project, where they were looking at the impact of cosmic rays and factors that affect it. I've provided all data links to Tom, so the graphs, should anyone want to, can be verified, or even some of the concepts I give extended. Let's just have a recap on the hypothesis of how cosmic rays influence our climate. I'll just move that a little bit. Cosmic rays are continually striking the Earth. Their intensity varies with attitude. They create nuclei due to the interaction with the atmosphere, which are fundamental to cloud formation. Clouds have a net cooling effect, and therefore they have an impact on our climate. The sun is the Earth's sole source of heat, but the fluctuation in solar energy is insufficient to account for the rise in recent global temperatures. That's really the Industrial Revolution time, which is about 1850 to current. Therefore, this, the classic line for any solar signal is that therefore this cannot, the energy rise we're seeing cannot be responsible for the current rise in temperature. But consequently, there must be a mechanism that amplifies the solar energy. They think, the classic narrative is that it's carbon dioxide acting as the control knob, whereas I'll be proposing, but they're not really my hypothesis, but I'll be giving evidence that other hypotheses are more valid. The magnitude of cosmic rays striking the Earth is controlled by their source, the sun and the Earth's magnetic fields. as the sun's magnetic field fluctuates, this deflects cosmic rays away from the Earth. Solar cycles are correlated to fluctuations in the magnetic field. Consequently, there is an inverse correlation between solar sunspot activity and cosmic rays, as shown in the next slide, next few slides. So hopefully this, picture paints 1,000 words. I'll just call up the laser pointer here, pointer options laser. And so this is basically just a good diagram of the first statement I made, how the solar and Earth's magnetic fields affect cosmic rays. So we've got solar winds. These are the magnetic fields coming in from the sun. They vary with the solar cycles, and they deflect cosmic rays away from the Earth. Then there's the Earth's magnetic field here, which is much reduced at both the North Pole and the South Pole, and the maximum deflection occurs around the equator. This is just the graph showing the impact. I showed these on my previous presentations, where we show the inverse relationship of cosmic rays and solar cycles. And you can see where cosmic rays peak, say here, is a good example. Solar cycles are at their lowest. So they were the takeaways there. So this is a recap. What are the difficulties of finding a solar and cosmic ray signal? This graph here, which was presented in the previous presentation, demonstrates the linear rise here for the black line. Again, I showed this before, and the green lines bars here are temperature anomaly. So we're looking at the temperature anomaly is where they attempt to take Berkeley Earth, try to take away the seasonal differences. Obviously, the temperature is a lot warmer in winter than in summer, and so they work on them by taking a monthly mean from 1950 to 1980, and take away each month value away. So it tends to reduce that seasonal variation. So that's the definition, broadly speaking, of temperature anomaly. These orange sort of brown lines here represents the mean seasonal minimum for the same period as I just cited, 1950 to 1980. And you can see that the actual temperature rise here is fairly small relative to the overall seasonal minimum. And of course, this is not the complete data set. Berkeley Earth, I don't think they're keen on showing you just how minimal the actual temperature rise is relative to variation. There's a slight degree of possible paranoia on my part, but they update it, I think, possibly every 7 years. And I noticed that some of the files still included, they used to include the full temperature variation. So if we just have a quick look at that. So this is the temperature variation for Omsk, which is in southwestern Siberia in Russia. And this is the full data set that they present, and it's 1887 to 2013. So again, I've given the black linear line showing the temperature rise for this full data set, and this represents the full data variation, and the green lines represent the temperature anomaly. Basically, it shows just how small the signal is here. So the point of me showing you this is to demonstrate just how difficult it is to find a temperature signal or a cosmic ray signal in these data sets. There's so much variation. What I'm looking for is direct comparisons with a direct correlation with temperature. Right. This was a graph I showed previously, where from Berkeley Earth. So fortunately, Berkeley Earth and some of the other sites present monthly data, which is going to, as you'll see, is absolutely vital to this the analysis I'm going to perform. And so we've got the 12 months data. I showed this all before, and basically the takeaways from this is that we're seeing much greater cycling in the winter months. So if you look at January, February, and March here, you can see there's much greater cycling relative to the summer months. And so the conclusion is that the the orientation of the Earth is having a big effect. And also we're seeing, clear cycling during these months, and that cycling diminishes in the summer months. And this is a graph of the an expanded graph of that January record, and you can see that I've overlain this again. I showed this before with solar forcing, with watts per meter squared here, plotted on the secondary axis, and the black line represents solar forcing, and there's a distinct correlation in the two, in that they seem to be tracking one another. I don't know what this is. They seem to be tracking one another, and if we do an analysis of the peaks, this works out at about 11.7 years, so the average distance between these peaks, whereas solar forcing, which is representing also solar cycles, is about every 11 years. So there's a distinct correlation over this period, 1850 to 2020. So data supporting temperatures solar cycle correlation. So just to consolidate on that, we're going to look at a mean of 4 locations from northern latitudes. All locations demonstrate clear cycling relates to solar cycles. In other words, this is a very consistent phenomenon. Here we have, so this is these from 4 locations that span the globe at a northern latitude around 60 degrees north. And I've compared, here we're looking at the January and July figures here. So we've got this is January, and once again, we're seeing clear cycling, and we're getting a much diminished signal during the summer months. This is just a plot again with this mean data of 4 locations overlaying. So it's just consolidating on what I did before, really. Again, we're seeing a pretty good correlation to solar forcing, where the two are tracking one another, indicating that the solar signal is being amplified by a mechanism, and that is the actual warming effect from the solar forcing is being amplified in the northern latitudes. This is also a comparison now of the southern and northern hemispheres in January, and you can see just how obviously there's differences in orientation of the Earth during this time of year, but you can see that just how powerful the cycling is in the northern hemisphere compared with the southern hemisphere, at least this time of year. I'm using a 5-year rolling average, which I'll use pretty well throughout, and that was you can see all the data points here to give you some idea how much the data is scattered, this maximizes the smoothness of the signal, and I'll use that virtually throughout my analysis. So just taking a step back on this theory of cosmic rays and the formation of clouds, just how strong is the effects of clouds on solar energy striking the Earth? Well, this is just some of a couple of articles I'm going to cite here. This is one from 1989 that was referenced on the NASA website. It was entitled "Cloud Radiative Forcing and Climate: Results from the Earth's Radiation Budget." And basically from these authors, I won't read those out, you can read it for yourself. The magnitude of the observed in that, I think this is from the abstract, the magnitude of the observed net cloud forcing is about 4 times greater than the expected value of radiative forcing from a doubling of carbon dioxide. The shortwave and longwave components of cloud forcing are about 10 times as large as those for carbon dioxide doubling. Small changes in cloud radiative forcing fields can therefore play a significant role as a climate feedback mechanism. So basically, these authors were concluding pretty much the basic theory of cosmic rays. If it can influence clouds, it can amplify the signal. And also it's all quite staggering that I believe that I haven't studied the IPCC website or the work they've done extensively, but they don't really, I believe, include the impact of clouds yet. It's a factor. It's a massive factor in our climate. If we now move to another article, this is one that was I suppose it seems to have been largely forgotten about. It was published in 2011 in rather aptly named Remote Sensing. And this is the role of effective cloud albedo for climate monitoring analysis. So they pretty well reiterate this. They say the net cooling effects of clouds is 10 times higher than the decadal anthropogenic radiative forcing induced by increase of greenhouse gases. Trends and changes in extremes of the cloud albedo would change the cooling effect of clouds, or therefore significantly affect the climate on a global and regional scale. Hence, the effective cloud albedo plays a dominant role in the Earth's radiation energy budget. Furthermore, this quantity can be observed from satellites without the need of any model or otherwise external data. And don't forget that when they're calculating the impact of greenhouse gases, this is largely based on theoretical modeling. So that when they state these 10 times, it's actually just really based on theoretical modeling. And anyway, so from this paper, the reason I cited this one is that they're actually doing satellite measurements as opposed to some theoretical modeling. And this is this is just a snapshot from part of the paper. And this is just to demonstrate just how dramatic the effects of clouds are. So this is satellite measurements taken over a 23-year period for what they term the Intertropical Convergence Zone, ITCZ. And this is a trend in cloud albedo, which is the top one here. And this is the trend in surface radiation. And the points I want you to take away here, you can see it's the coast of Africa. And the point you want to take away here, this is data, as I said, averaged over a 23-year period. They had various calibration mechanisms to try and ensure that the data remain consistent over that period. And you can see that there's an inverse relationship with the two. As there's a decrease in cloud albedo, there is a warming effect. And also you can see that over the oceans, there's a very distinct warming effect, as opposed a very different effect over land to over the oceans. And this is quite interesting, and I'd like you to try and bear that in mind when I move on with this talk. And they also say they conclude there are quite dangers in taking just land measurements, which a lot of the climate scaremongering relies on. But anyway, just bear that in mind, and I think this really does demonstrate on just how powerful the effects of clouds are. So, is there an effective way of demonstrating a direct correlation between temperature and cosmic rays? The data I presented previously, trying to look at a correlation with cosmic rays and temperature, was not as convincing as I was hoped. I was hoping to get a better correlation. As I said, this is quite a challenge. This was the data I actually presented. What we were looking at here was the rate of change of cosmic rays for Oulu, Finland, against the rate of change of temperature. And I've also put in here a polynomial first order fit just to provide, because it seems as though they curve. As we look down the bottom axis here, we're looking at the monthly rate of change for each month, and then we've got the temperature change here on the secondary axis. So this is this orange line here. So we're getting the lowest rate of change in the summer months for temperature, and the highest rate of change for cosmic rays in the summer months. So they directly oppose one another, as do the polynomial curves. And this all agreed with the theory, but as I said, it wasn't quite as convincing as I would hope. Just to outline what the problems are with trying to look at a correlation between cosmic ray measurements and temperature. This diagram here depicts it. So what we're looking at here is the cosmic rays are coming in, they're striking the Earth's atmosphere, and then we get these secondary effects, which includes the neutrons. And that's what we actually measure at ground level. In this case, it's Oulu, Finland. And the reason I took Oulu, Finland was because it was one of the longest data sets. And I've not really been that successful at getting up the data sets, but so I've used them. And also there's a temperature record also from them from Berkeley, Earth. So that's basically the theory. So what we're actually interested in is the interaction with the atmosphere. We're not really interested in what's happening at ground level. But if we go back to the previous graph, it does appear that the variation is correlating with temperature in a manner that's in accordance with the theory of the main proponents are Neer-Shaviv and Henrik Svensmark on the impact of cosmic rays. So what we can do is we can look at the variation of cosmic rays. What I'm going to do now is look at the variation of cosmic rays in more detail by taking a rolling standard deviation every year and compare that with the temperature. And this is the plot we get. Oh, sorry, no, I'll take a step back. Just to show, what we're going to try and do here. Is there an alternative way of looking at the cosmic ray data? So to look at it in more detail, what I've done here is this is a plot of the variation of cosmic rays as determined by standard deviation. So standard deviation is a statistical measure of looking at variation in a data set, and this is cosmic rays. And as you can see, there's an inverse relationship between the cosmic rays and deviation. So when cosmic rays are at a low, the deviations at a high, and when cosmic rays are at a high, the deviations at a low. It's not a perfect fit, but it seems to correlate pretty well, and that's what this graph is showing. So an explanation of that is that an application of variation of cosmic rays. During high periods of elevated solar activity, cosmic rays are deflected away from the Earth by the increased solar magnetic fluctuations. The low-level magnetic activity is relatively stable, whilst increases are more variable. Consequently, deviation from the Earth of cosmic rays is more variable. This is due, to the solar flares being much more random. Assuming we can track this variation at ground level, which was indicated by the previous graph that I put in my previous presentation I showed you, we can compare it with temperature variation at the same location. We might be able to see a correlation. So I did that, and I plotted that, and I came up with this graph. So this is a temperature anomaly on the primary axis, and this is the standard deviation of cosmic rays. So we're looking at the variation of cosmic rays striking the Earth. And so that is represented by this green line, and the orangey brown line represents temperature. And as you can see, there's a pretty good correlation at this specific location, Oulu, Finland, for both a temporal correlation and a pattern correlation more than anything. I suspect you can apply various statistical functions to this, but I'm just using a visual comparison for the viewer that they can judge for themselves whether they think these two are tracking one another. It's not a perfect correlation, but the pattern's there. And to me, this is strong evidence that cosmic rays are having a direct impact on temperature anomaly in this part of the world. So could these techniques of enhancing the solar signal be applied to other data sets? The sea surface temperature data record has received a considerable amount of analysis, including the primary author of the hockey stick, Michael Mann. He did quite sort of tried to do some quite sophisticated methods of trying to track whether the sea surface temperature data was cycling. I think he had about a 60-year cycle he came up with. He didn't find anything at 11 years for some reason. I don't quite understand why. And Judith Curry, who's also appeared on Tom's podcast, has also she's done quite an extensive article on the hunt for various cycling within the sea surface temperature record. I had not looked at sea surface temperature data other than a brief examination in my previous presentation, where there was a paper by Holgate in 2000 where they were looking at the rate of change of sea surface temperature, and that was correlating rather interestingly with solar cycles, although he didn't even bother to mention in his paper. And this was pointed out by Jasper Kirkby. I referenced him in the previous presentation. So what I did was I applied these signal enhancing principles that I've just outlined of using the variation to the national, this is all a bit of a mouthful, the National Oceanic and Atmospheric Administration, that's NOAA, with the Atlantic Multi-Decadal Ocean Sea Temperature Data, that's AMO, as the acronym. So if we just have what is this strangely named Atlantic Multi-Decadal Oscillation? It's an extensive data set from the NOAA website covering monthly sea surface temperatures from 1856 to 2022. We've got to bear in mind variation will all change over time. Obviously, temperature measurements have improved to the extent now, I guess, they use satellite data. And we've got, the calibration methods will have improved. But I don't think that negates from the type of analysis I'm going to do. Well, why do they call it the Atlantic Multi-Decadal Oscillation? Well, on the website, they give these various diagrams, and you can see here again, there's the area. It's slightly different time. I think it's quite an interesting site. You can scroll through it. But basically, if we go down into this bottom area where I'm putting the laser pointer, you can see that goes through warm phases and cool phases, and they're about 35 years. And I suppose that's why they call it the multi-decadal oscillation. Possible pluses and minuses of using the AMO sea surface temperature. It's a colossal mass, so variation may be reduced average. This could mask a signal for all we know. How responsive are ocean temperatures to seasonal variation? If we're not getting much variation, it's unlikely we will see anything. Here is a plot of the monthly temperature data taken directly from that site. And you can see that the coolest temperatures are not surprisingly, in the winter months of December and February, and the warmest are in August and September. And they all seem to pair, which is probably indicating just the way as the sun goes around the Earth, that there's a sort of a distribution about them. The coolest and warmest periods. So the following is what I'm going to do. Is I'm going to plot AMO monthly sea surface temperature. This is the unsmoothed and detrended data variation using a 1-year SD from 1856 to 2022. So it's a nice big data set, and this is what we get. And so again, this is analogous to what we saw with the Greenland temperature data I showed you earlier, where we've got each month, and it's absolutely vital. It's a real plus that they gave this data to us as a monthly record. And so we're looking at the monthly change over this period, 1856 to 2022, and you can see in this sea surface temperature data, there's clear cycling in every month, and we can see. And the other takeaway here, from just looking at the overall monthly data, is we're getting much bigger cycling in the summer months than we are in the winter months, which contradicts what we were seeing for Greenland, which was quite well. They're opposing one another, and I'll explore that later. But just to do some basic analysis of seeing how well this cycling data, correlates with solar cycles. So what I've done is taken one of the months here, March, and I've correlated that against a sunspot number this time, and which is just again a basic measure of solar cycles. And I've compared the dip, and so the dip is the distance between the mean dip between each of these, and the peak data. So that's between for the sunspot number is between each of these peaks. And so for the mean peak is 11 years for the temperature data, and the mean dip is 10.9 years, and that correlates exactly with the solar cycle data. They're not exactly aligned, but there must be some sort of carryover effect. But there's a very, very strong correlation. If we go back to this, you can do just a crude assessment of counting the number of peaks and compare it with the number of solar cycles over the same period, and typically there's 14 or 15 for each of them. So if we now look at another month, this is April, just to reiterate the point, you can see that they were all cycling. We get a mean peak at 10.6 years for the temperature record, and a mean dip of 10.5 years, compared with 10.9 and 10.9 for the sunspot numbers, representing the solar cycles. I've taken exactly the same period available. That's why there's a slight difference, but not much. If we compare, just to do some overlay graphs of the point that there was a difference between January and July, there was a clear trend, a monthly trend, and this is just to reiterate that point. So we've got in blue here the January sea surface variation against the July variation, and you can see that July is cycling more strongly than January, but both are cycling quite clearly, as I showed in the monthly data. If we now plot a comparison of variation as measured by standard deviation of the temperature with the Atlantic multi-decadal oscillation with Greenland for the equivalent periods, the sources NOAA and Barclay, we can see. So what I've done here is that these are the lines here represent each month's variation, and on the secondary axis is the temperature anomaly, and you can see they directly oppose one another. So for Greenland, and then I've applied, and this time, a second order polynomial fit on this. So, and the purpose of just using that function is to give us a consistent curve fit, and so we can compare the two data sets, at least in terms of a curve, in exactly the same way. But you can see the dots are fairly consistent for the raw data points for each month's variation that we're seeing in the temperature record and the temperature anomaly. So they oppose one another. So in other words, it's varying much more than the maximum variation for the Atlantic multi-decadal oscillation is in August, whereas for the temperature anomaly for Greenland, it's minimal in August. And but perhaps a slightly better way of representing this data is look at the warming rates of each. So it just gives you the relativity of the two. So here I'm plotting the warming rates for Greenland and the Atlantic multi-decadal oscillation. And we can see that, the first takeaway, which was presented in the previous thing, is that, there's about 6 times the rate of warming in over this period, 1856 to 2020, in Greenland in January as compared with July. So it's a massive difference. But that we don't see that difference so much in the Atlantic multi-decadal oscillation. But what we do see is a gradual approach through the summer months of towards the same rates as we work through the year, and then obviously a decline and a climb back up as we go through to the winter months. Well, what's responsible for this? Well, almost certainly we know that in the oceans or warm, both the oceans and the atmosphere have currents that warm the land masses. For instance, UK, where I live here, is we're warmed by about 4 to 5 degrees for equivalent latitude. Say in Stockholm, we're about 4 to 5 degrees warmer than equivalent latitudes. So what we're getting here is, it appears, is that the warming occurs at the equator, and we're getting currents shown here from this diagram here, coming up to Greenland here, to the landmass of Greenland. So basically, we're seeing this. So just to give a quick quote from Einstein, no amount of experimentation can ever prove me right. A single experiment can prove me wrong. So it'd be good if some of the climate change scientists stuck to that. But anyway, that's another story. So the concept of winter heat transport, it explains why we can see such a strong solar cycle temperature signal in the northern hemisphere, as land warming temperature variabilities reduce considerably during the winter. In other words, there's hardly any sun. The differential between the sea surface temperature, atmospheric currents, and the land temperature is amplified. Hence, the cycling is evident due to the inherent solar signal in the ocean, and is more pronounced in the winter months in the northern hemisphere. Just to illustrate that point, this is available from NASA /CERES. This is global pictures of solar incoming radiation. And so we've got December, January, and February. And so during the winter months, you can see it's not really surprising. They only get an hour of twilight, in the very far north, but there are big differences, and then as we go through to summer, it's reversed. So this is what's responsible. So if we're looking at the North Atlantic and coming up towards Iceland, it would be coming up here. So this would be the temperature gradient in the winter months, and this would be the temperature gradient in the summer months for the northern hemisphere. Again, to take a step back, if you reflect back on that data I showed you with clouds from that paper from 2011, why is sea surface temperature variation so impacted by cosmic rays? Well, this was published in 2021 on the CERN website, which they had a project called Cloud, where they were looking at the effects of cosmic rays with a chamber with various different atmospheres. They could adjust that atmosphere very accurately, and they concluded just let me move that down. They concluded that in their site, rather strangely, I thought, talk about sticking to the accepted narrative. These are massively expensive projects, and their funding must come from governments. So they really do have to adhere to the narrative. But in that, they actually wrote in the headline from that when they were reporting the results on the site. They said the results suggest a new mechanism that could accelerate the loss of Arctic sea ice. Well, I don't quite know why they concluded that, because to me, the takeaway was that there were other factors that over marine environments we were going to change. So just to see what the actual site said, in a paper published on the 5th of February 2021 in the journal Science, the cloud collaboration at CERN shows, this is taken directly from the site, at CERN shows that aerosol particles made of iodic acid can fall extremely rapidly in the marine boundary layer. So that's one of the key takeaways here. The portion of the atmosphere is in direct contact with the ocean. Aerosol particles in the atmosphere affect the climate both directly and indirectly, but how new aerosol particles form and influence clouds and climates remain relatively poorly understood. This is particularly true of particles that form over the vast oceans. So if we reflect back on those cloud boundaries over the land and the sea, and then we reflect on this data, the sea surface temperature, we can see this really all tying together. The iodic acid particles have been observed previously in certain coastal regions, but we did not know how important they may be globally, says cloud spokesman Jasper Kirkby. Although most atmospheric particles form from sulfuric acid, so that was another molecule they found that was influential over cloud condensation nuclei. Our study shows that iodic acid may be the main driver in pristine marine regions. Anyway, so really, I think a lot of that, as I said, ties together. So I'm proposing, I think pigs might fly, but these graphs from reputable sources, that from massively pro-climate change narrative sources, should replace the famous hockey stick graph. So just as a quick, I'm going to do a quick summary of the graphs I've presented. This is graph 1 from Berkeley Earth NASA. This graph clearly demonstrates a dominant solar cycle signal that accounts for a significant proportion of temperature change in the northern hemisphere. This relates to solar cycle, cosmic rays, and heat transport. So we're seeing the two tracking one another, and it's a powerful evidence that solar cycles are having the solar activity in conjunction with cosmic rays is having a powerful effect on our climate. The second graph, which I presented, shows this graph demonstrates a clear visual and temporal correlation of cosmic ray variation and temperature anomaly for Oulu, Finland. I'd like to have had another data set, but I couldn't find another one just to add confirmation to this. But anyway, I think there's a strong correlation between the two, both in terms of the visual pattern and the temporal correlation. Graph 3 from NOAA, again, this was the data I did on the cycling that we're seeing in March of the sea surface temperature aligns hugely with the sunspot number, once again indicating the influence of the solar signal. Graph 4, this is slightly separate data set. This was the stuff from Holgate that I referenced previously, but it's a separate data set. This is looking at the correlation in sea level rise. So it's not sea surface temperature, it's sea level rise. And once again, we're seeing a correlation between the solar cycles, in this case, in the term of sunspot number, and the rate of sea level rise change. Graph 5, this graph compares the monthly variation in the North Atlantic. That's the Atlantic multi-decadal oscillation in Greenland. There is a clear reversal of trends indicating the significant role of heat transport to Greenland from the ocean atmospheric circulation. This graph compares monthly warming in the North Atlantic and Greenland, so same data again, but this time we're looking at warming rates. We can see that there is evidence as this approaches, the heat differential, the warming differential is so great that we get this amplification of the signal in the northern hemisphere, which we've seen consistently throughout. So conclusions, there is considerable amount of data from independent sources. So these data sets are coming in from everywhere, and they all indicate the influence of the sun's activity via cosmic rays and ocean atmospheric heat transport. The data I presented amalgamates really the hypothesis of Henrik Svensmark and Neil Charest on cosmic rays, and Javier Venus on his winter gatekeeper hypothesis. The proponents of these two hypotheses have provided extensive additional evidence. The graphical evidence provided in this presentation, taken directly from organizations that are supporters of the climate change narrative, provides a more plausible explanation for the current rising global temperatures other than the CO2 narrative, the carbon dioxide narrative. And basically, one of the key takeaways from this is the science is always unsettled. So thanks very much for listening to this presentation. And I'd like to finish it with a question to Tom. Tom, if you had to defend you're pretty knowledgeable, you've listened to very many people with various ideas on climate change. If you had to defend the narrative, if your income, livelihood, career, reputation depended on defending the carbon dioxide narrative, anthropogenic climate change narrative, what would you go for?
Great question. I don't see any way to defend it in any way. I don't know. What do you think? There's no defense.
I don't have I like to think I'm fair-minded with, that's the whole point of science, is you consider black swans, you consider other data, what is the supporting data? And I don't think there's anything.
Yeah, I mean, I like the idea of trying to steel man what they are saying, but whatever. I do think it is warmer since 1850 and it is warmer since 1975, but so what? And then the whole idea that the weather is getting worse, they're trying to convince us fires are getting worse and cyclones and blah, blah, blah. But yeah, I keep saying I've gone down all of these rabbit holes and there's nothing anywhere. There's no signal of anything that's unusual or bad happening now that's caused by CO2.
Yeah, so I don't know what will ever, one of the beauties I would like to think from this presentation, I don't have the intellect of many of your presenters, that's for sure. But what I do think is the beauty of this is I'm taking direct data. It's just some simple statistical functions on data from massively pro climate change narrative sites, as I stated on the side during the presentation. And it points in a completely different direction.
I really like the fact that what you're saying, if I get this correct, is that basically the cosmic ray theory is basically correct, and the winter gatekeeper. The data supports both of those things, correct?
I think so. I think that is exactly what I'm trying to say. I think both of them are correct, because they've both presented a lot of convincing data and evidence in support of both theories.
All right. Then my final question. Go ahead.
Yeah. So, well, I was going to say, this doesn't negate, of course, other cycles like Milankovitch cycles and other things, because it's just an amplification of the solar signal. So, you've had other presenters, I think, what's his name? Weiss, I've forgotten his Christian name. He was
Carlotto.
He was showing other cycles, wasn't he? And this is all, this doesn't negate those either.
Speaking of that, you were talking about how I think changes in the Earth's own magnetic field can change cosmic rays and change cloudiness and change the climate, right? That's yet another way the cosmic rays can get affected. Changes on the sun or changes on the Earth.
Yes, because the magnetic field is so much stronger at the equator than it is at the poles. That will have a bearing, and that is fluctuating. But I haven't seen a lot of work on. I haven't read much at all on that degree of fluctuation. It's all really to do with the solar magnetic field fluctuation on what I've presented. seems to be one of the dominant factors. But there'll be other factors as well. This trace level molecule that that Jasper Kirby's team were identifying, that's clearly going to have a bearing. Anything if you can get just trace level, I think it's parts per million in the atmosphere, that can affect cloud condensation nuclei, that may well have a great bearing as well.
From what you've seen, do you have any ideas about what's going to happen in the next 50 years to Earth's climate?
No, you asked me that last time, and I think trying to make any predictions about what's going to happen, I think it will track solar cycles. I think the narrative simply won't be supported because we've got a really quite accurate satellite work going on. There's no way it's going to support the climate change narrative, and then we get more and more desperate as the data moves away from supporting the narrative.
All right. Any other points you'd like to make before we go ahead and finish up here?
No. Thanks for your time, Tom, and hopefully I'll meet you in person someday.
That sounds fantastic. All right. Thanks a lot for all your work, Stephen Andrews. Talk to you next time. Bye.
Thank you very much. Bye now.